Okay, welcome everyone to this continuation of tropical geometry. What is tropical geometry? And today I would like to zoom in literally on the first type of applications that we see in what tropical geometry can be used for. And I would like to do some kind of a modern topic, a trendy topic, whatever you want to call it, neural networks or artificial intelligence. And I'm kind of want to make the point, which is not me making this point, that, I'm just recalling it, that tropical geometry is kind of the underlying language of artificial intelligence or neural networks or whatever you want to call it. So let's have a look at the corresponding paper. So if you Google something like tropical geometry neural networks, there's kind of a very nice paper, this one here, and that's the one I'm going to summarize. So it's a really nice paper, and it has everything I'm going to tell you about it. It's really more like a math paper than a neural network paper. So if you are kind of a mathematics type person, you will like it, but it's also a computer science type paper. So if you are a computer science type person, you will hopefully like it as well. So let's have a look at this. I'm kind of assuming that you at least are mildly familiar with neural networks. If not, I will at least give you a sketch what they are. A super brief reminder, really, literally. So a neural network is nothing else than a function with some inputs and some outputs, and a function has some process in between. And usually it looks like this. You have some inputs, you have some weights, you take a sum over the weights. So essentially it's a matrix type operation. And then you have this fancy activation function, and I will show you in a second why you want that. So here you have a linear thing, completely linear, and here you have a non-linear thing usually. So an activation function. So activation functions come in many different many different flavors. The most popular one, let's see, non-linear. Let's zoom out a little bit. Mathematical details, comparison of activation functions. So you have the most famous one probably today is ReLU, which is this little function, the blue one, which we will see in a second again. And there are variations, as you can see. This one is a smooth version. So GALU is maybe the most used one nowadays. It's a smooth version of ReLU. But I will stay with ReLU in a second, or WellU, or whatever people want to call it. And there are several others. As you can see, there's a whole zoo of those activation functions. And the point is they're all non-linear, whatever. And the hyperbolic tangent was very popular for a long time. And the logistic sigmoid, something like that. Some non-linear functions. The identity is sometimes also used, but we'll see in a second. And that's a linear function, by the way. We'll see in a second that that's actually not necessarily very useful. So a linear part, the first one, literally a function where you take sums over entries, that's a linear thing, and then you apply some activation function on it and you get some output. That's a very simplistic version of what a neural network actually does. Yeah, so every layer, so these guys are called layers here in the middle, is a linear map. Strictly speaking, an affine map, if you know the difference. If not, just think of it as a linear map and some kind of activation function. And for me, it's usually, at least this is kind of the easiest one you can think of, the ReLU gates. Yeah, and I would like to recast that in the language of tropical geometry. Because the way how ReLU works, it's a max plus instead of the min plus I was always using. That's not really a big difference, but yeah, just be aware that this is better to be recasted in the language of max plus instead of min plus. But don't worry, I will recall in a second what that is. So here is our ReLU that we just had. It's a nonlinear function. And it's literally just max of 0 and x. Yeah, it's identity on the positive part and it's 0 on the negative part. And as you can see, this is not a linear function. It's a piecewise linear function. It has this little kink here, right? Kink, breaking point, whatever. So linear and then linear, but at this point, it's not a linear function. Yeah? It's a piecewise linear function. And if you apply a linear function, let's say if you go back here, a linear function, and then a piecewise linear function, you get a piecewise linear function. So actually, every of these processes is a piecewise linear function. Piecewise linear function, which literally just means, well, hopefully that was reasonably clear in this lecture on tropical geometry. There's something tropical going on. Yeah, there's some polyhedral thing. I will show you in a second a nice way of thinking about this. So kind of polyhedral thing, and we want to just rephrase this in a max plus algebra setting, because tropical geometry, polyhedron, piecewise linear functions, that is what tropical geometry is all about. And let me just show you why you want piecewise linear functions. So the best way nowadays to think about or talk about or learn about neural networks is the TensorFlow playground. So TensorFlow playground, very nice. So neural network. Let's make it a bit bigger here. So here are the various layers. So input, output, and here's one of the ones in between. So here are the weights. So, and here are the neurons, right? So neurons are kind of the outputs where you take the sum. So every neuron is the sum of the ingoing weights, and then one of the activation functions that you can choose here, right? You have kind of the standard example that I just showed you, ReLU, hyperbolic tangent, sigmoid, or just a linear one. Don't worry about the other things that's going on here. And the task here is, so let's just do that one, to, well, distinguish the blue points from the red points. And if you just train this neural network, our little linear neural network, linear activation function, everything is linear, will do exactly what you think you should. In order to distinguish those points, you draw a line in between them, right? Yeah, and here you would, you can't really draw a line, as you can see, so it already fails. And here, you can't draw a line either, so it kind of tries to draw a line, right? It's a linear neural network, but it can't do this. And this is exactly why you need those activation functions. The world is not linear. A linear function will not get you anywhere, at least in this setting. It should approximate this problem, but it can't, right? How would you approximate this problem with a linear function? You would need to draw a line somewhere. I'm not sure how to do that, but if you just change your activation function, you will see what's happening, and it will draw a polygon, right? That's the whole point. So ReLU this piecewise linear thing, and now it will draw a polygon, which is a piecewise linear object. And this is exactly why you use these type of activation functions. Here, it will draw this piecewise linear beast. This one is a bit trickier. It will eventually, so this one needs a bit of playing around because it's a bit trickier. As you can see, it tries to draw a polygon. This one is literally boring, of course. A line is also a polygon, but I like this example. So literally, it will discover that a polygon is a perfect approximation on, or a good approximation to a circle, right? Multi-layer polygon. And that's why you want some nonlinear function here, right? The rest linear and then a nonlinear thing. So if you would use something smooth, you would get something smooth approximating it. That's also fine, but I like this one because it's so simple and so easy. Let me just pull it up again, right? So ReLU, just this easy function, max 0 plus. So all of artificial intelligence, if you want to summarize in a nutshell, it's a bit of a lie, but it's fine for today. All of artificial intelligence is just a piecewise linear approximation using this stupid piecewise linear function and, well, linear functions. It's kind of nice. Okay, and that's like, looks to me like tropical geometry. And the gentle version for what we really need is a tropical rational function. So here's the plot of a tropical rational function. It's like this piecewise linear stuff everywhere, right? So you have a plane glued to a plane, glued to a plane in a slightly fancy way, right? So tropical arithmetic was this one, hopefully remember, except that we had min, but for this one max is a little bit nicer. A tropical polynomial is exactly that thing, max of an affine form essentially. And a tropical rational, so usually a rational function would be a polynomial divided by a polynomial. Well, now our multiplication operation is addition, so a tropical rational should just be a tropical polynomial minus another tropical polynomial, right? That's a tropical rational function. Here's an example of how these look like. And then the main theorem is, for ReLU networks, these are the piecewise linear ones, these are essentially all you need. ReLU networks are the same as tropical rationals. Well, there's a one-to-one correspondence between tropical rational functions, wow, that's a complicated name, tropical rational functions and ReLU networks, right? Every ReLU network is a tropical rational function and vice versa. It's kind of a nice result. It's kind of a really nice result. That's all you need, ever tropical rational functions, right? So you study tropical polynomials in tropical geometry, and of course you also study tropical rational functions. in tropical geometry. Right? It's kind of a nice, the main theorem of this paper here. Where is it? Proposition theorem. Equivalence of neural networks and tropical rational functions. They explain that very carefully. It's really straightforward. It's actually not very difficult. It's kind of a cute and nice observation. It's really nice. So neural networks, essentially all of artificial intelligence, is some version of tropical geometry, which you might think should give you some type of applications, right? So you can just think of those networks as being part of tropical geometry, and of course, then you get various different type of applications in artificial intelligence just by translating it into standard questions of tropical geometry, whatever, tropical hypersurfaces or something like that, some object like on the top here. Anyway, I hope you enjoyed this video, and I also hope to see you next time.